Hello everybody, I'm Aditya Srivastav and I'm here to present our team's work on the lab high performance CUDA programming on Google Cloud. The lab consists of 8 different parts and I'll be walking you through the first 7 parts. The first part includes a CPU matrix multiplication performance analysis. We implemented a matrix multiplication using C with O n cube complexity. We observed that the time complexity was verified as cubic and doubling n increases the time around 8 times. The performance peaked at nearly 1.7 gigaflops for n equals to 512 to 1024. The performance degraded for large matrices due to cache misses and memory limits. We identified that the CPU bottleneck was memory bound, not the compute bound. The figure 1 shows the plot between the execution time and the matrix size n. The part 2 comprises of the naive CUDA GPU implementation. Each GPU thread computes one output matrix element. We used an NVIDIA Tesla T4 on the Google Colab with CUDA 12.x. We observed the speed up to 24,000 times for large matrices n equals to 4096. We detected an anomaly. The GPU time was nearly flat due to the measurement or the utilization limits. The GPU was beneficial for n greater than 512, where the speed up was exceeded nearly 10 times. The figure 2 shows the comparative performance between both CPU and the naive GPU. The part 3 comprises of Google Cloud GPU implementation. We deployed a naive kernel on Google Cloud platform, which was a Tesla T4 and on an Ubuntu 24 machine. GPU performance followed expected O(n)cube scaling. The speed up was up to 608 times more faster than compared to CPU, achieving nearly 316 gigaflops. The GPU was limited by memory bandwidth and it only utilized 4% during its peak compute. The GCP showed correct scaling, unlike Colab, with stable dedicated resources. The figure 3 shows uh, the performance analysis of Tesla T4 GPU. The part 4 comprises of optimized CUDA implementation with shared memory tiling. We used around 16 cross 16 tiles with shared memory to reduce global memory access. We reduced the global memory traffic by around 87.5%. We achieved 1.5 times speed up over the naive GPU kernel. We improved the gigaflops from 320 to 433 and the GPU utilization rose to nearly 5%. Modern GPU cache systems reduce the theoretical tiling benefits. The figure 4 shows the 3 comparative study uh, between CPU, the naive GPU, and the optimized GPU. The part 5 comprises of cuBLAS performance comparison. We compared our kernels with NVIDIA's cuBLAS library. The cuBLAS achieved up to 2843 gigaflops, which is 35% utilization. Our optimized kernel reached nearly 433 gigaflops, which is 5% utilization. cuBLAS was 6 to 7 times faster due to multi-level tiling, register blocking, and warp optimization. We concluded that the professional libraries always outperformed the academic implementations significantly. The figure 5 shows the the comparative study amongst CPU, the GPU, op GPU, and cuBLAS. And the columns CPU to cuBLAS, naive to cuBLAS, and op to cuBLAS show how much performance increment was there from doing a transition from this CPU to cuBLAS or naive to cuBLAS or op to cuBLAS. The part 7 was the performance analysis and different questions were answered. Our implementation shows O and cube scaling amongst the CPU, GPU, and cuBLAS. GPU was 100 to 800 times faster than CPU for n greater than 512. The tiling optimization adds 1.5 times average improvement over the naive CUDA. A kernel achieves up to 83% of cuBLAS performance for small matrices. cuBLAS still leads due to the multi-level optimization and hardware tuning. Now over to Mohit, who will be explaining you the practical implementation of part 1 to part 7.
So initially we see that we have Tesla T4 with 15 GB of memory and running about 60 degrees. Now let's quickly look at it, a quick demo, right, to understand what's going on and what are the tests made of. So the naive version uses basic CUDA parallelism where each thread computes one output element, and the optimized version loads 6 by 16, 16 by 16 tiles into shared memory to reduce global memory access. And the cuBLAS is NVIDIA's professional library with years of architecture specific optimization. So all three work correctly. We notice that the checksums are in the same range. These are randomly generated, right? The inputs of the matrix, this is randomly generated, and the checksum is in similar range, so we get to know that it is correct. Now let's quickly move on to the next comparison, which is a full benchmark. So here we compare from 256 by 256 all the way to 2048 into 2048, which is from 65,000 to about 4 million entries. So here we get a clear idea of the outputs. So initially the difference is not much. In fact, the cuBLAS has a higher time because of overhead. But as we move to larger matrices, which is what we encounter in real world, the difference becomes completely clear. The naive and optimized versions have larger and larger time, while the cuBLAS has much better time getting a good output. So, and this is what happens in real world, right? There are large matrix multiplications that are required, and cuBLAS has the best output. Let's see a quick comparison demo so that we can visualize how much speed up is happening in all three formats of GCP acceleration. So now in these values it becomes completely clear, right? Initially the speed up isn't much. In fact, it's even lower. The cuBLAS speed up is lower, but once we move higher up, we clearly notice the speed ups of cuBLAS over others.
Hello, I am Krish Modi and I will go over the demo focused on efficient 2D convolution with GPU acceleration. I'll walk through the code architecture and show you the performance results obtained from running on Google Cloud with a Tesla T4 GPU. This file is modular and library focused. Both CPU and GPU functions maintain the same API, supporting arbitrary matrices and filters. The code is designed for easy Python C integration, enabling robust and flexible benchmarking or deployment. The CUDA kernel uses a 2D organization where every thread computes exactly one output pixel, making the code general and scalable for any image sizes. By encapsulating all GPU memory management in the library, we prevent leaks, simplify multi-language integration. This architecture also makes it easy to upgrade individual kernels without breaking the library interface. The test framework is designed for robust automated benchmarking. It uses C-type to interface with our CUDA library, ensuring type safety and memory layout compatibility. The statistical approach with multiple runs per test eliminates timing variance, and the comprehensive test matrix covers real-world scenario from small thumbnails to large 4K images. This automated pipeline eliminates manual testing errors and provides reproducible results. The MSE validation ensures a GPU implementation matches CPU behavior exactly. The visual outputs makes it easy to verify both functional correctness and performance gains. Everything from timing to plotting to data export is automated, making this suitable for continuous integration or research workflows. This slide this slide demonstrates the output of all implemented filters on a checkboard test image. Edge detectors respond only to certain transitions, while blur and sharpening have a strong, distinct impact on image detail and contrast. The visual result matches theoretical filter effects, serving as a qualitative correctness check. These benchmark plots validate our CUDA implementation. The GPU shows dramatic speedups even for moderate image sizes, and performance is robust for all filter types. The speedup level and scaling closely match theoretical expectations, supporting the case for production GPU deployment. Thank you.
The live demo of the convolution part 8. So let's initially build the file. So let's build it. So this builds the CUDA shared library, which is libematrix.so. By compiling the CUDA source code, which is matrixlib.cu, using NVCC and the corrected flags for shared linking. This step is essential for enabling GPU accelerated functions and making them accessible from Python. So next you can install NumPy for efficient array operations. So you can download multiple different dependencies from pip or apt as per your choice, and then you can also add matplotlib, which is used for generating plots, and pillow for image manipulation and IO, and pandas for structured results and CSV handling. We've already installed this, so we won't be running this. So next, let's run the complete Python test suite. So we have this file test library and we run this. So this does benchmarking both on CPU and GPU convolution via the compiled shared library. It will generate all tables, performance numbers, and the plots needed for the analysis. And the output you can see here is a comprehensive benchmarking and validation of both the GPU and CPU convolution implementations. It automatically runs the performance tests across various image sizes and filter types and generates key plots comparing CPU and GPU execution, and validates correctness using metrics like mean squared error. CSV files and comprehensive plots are produced for the report, and this output is significant because it not only quantifies the actual accelerated achievement by the CUDA implementation but also ensures correctness for facilitates reproducibility, and supplies visual evidence of the functional and performance improvements. So you can see all the files. There has been the PNG files formed here from the test suite that we ran.